This is screencast number 6, and we open with a very familiar refrain. It has to do with form and function, or the phrase structure determines function. And here we're going to be looking at how the molecular structure influences the strength of bonds and therefore influences the strength or weakness of different acids and bases. And we begin by looking at the acid strength of hydrogen halides. Remember, halides would be fluorine, chlorine, bromine, and iodine. We generally do not think of astatine because it's so rare and therefore not a big factor. The point we're trying to make is that when we observe the strength of these acids and plot them out in the halogen column, we see that our weakest acid is hydrogen fluoride and our strongest is hydrogen iodide. Again, remember that the strength of the acid is inversely proportional to the pKa, something we'll look at in a few minutes again. And interestingly enough, even though hydrofluoric is the weakest of the acids, hydrofluoric does etch glass, whereas the strong acids will not. Now, we have to explain why. Why is this trend right here true? Now, there are two kinds of things that we have to think about when we look at these halogenic acids. And one of them has to do with the energy it takes to break the hydrogen-halogen bond. X represents our generic halogen. And then once you break that bond, that would be the first part. And then the second part, we have to transfer the electron from the hydrogen to the chlorine or fluorine or whatever it happens to be. And as a result, the halogen ends up having an octet. Those both involve energy, and we have to offset the one energy against the other. Remember, receiving energy, the energy it takes to receive an electron, I should say, the energy involved in gaining that electron is often called electron affinity, which we had a long time ago. So the total amount of energy involved is going to be the result of taking these two kinds of energies into consideration. How much energy does it take to break the bond between the hydrogen and the halogen, bond dissociation, and how much energy does it take to transfer the electron from the hydrogen to the halogen? These two factors can sometimes work together, and sometimes they work in opposite directions. It all depends. And you can see some of those variations right here in this chart. You can see sometimes the bond dissociation energy is positive, and sometimes it's negative. In this case, at least they're all positive, but decreasing. And then over here, transferring the electron also generally decreases from here, but again, your hydrogen fluoride is very, very different. And the net effect gives you the total amount of energy. And look how much more energy it takes to split apart hydrogen and fluorine from each other than these others, which is why hydrofluoric would be considered a weak acid and all these others would be considered a strong acid. And then this chart off to the right, we'll look at in just a minute because we want to come to the top of the next page and look at this diagram of energy or enthalpy diagram, breaking this down into even further detail. If I have a halogenic acid right here, notice that the first thing we need to do is go from it being dissolved in a solvent to not being dissolved in a solvent. Now, the solvent happens to be water generally, so we could talk about the enthalpy of hydration But if we're going to be generic, we would talk about the enthalpy of solvation. When the solvent, again, is water, we use the more specific term hydration. Then, once we get our HX, our hydrochloric, or whatever the vapor is as a gas, then we have to separate it. We've got to break that bond between the two. Both of those steps require energy, which is why your arrows are going up, increasing energy. Then, once we have hydrogen atoms and halogen atoms, we realize that the electron in the hydrogen atom is going to be transferred to the halogen in order to make it an octet. As a result, I end up with a hydrogen ion, otherwise known as a proton, and my halogen with its 8 electrons. So that would be my chloride, my fluoride, bromide, or whatever. And then as a result of that, remember they're still in the gaseous state, now we're going to re-dissolve them. And we're dissolving them in water like normal, we would say the energy of hydration, not solvation. And we end up back down here. And all of those little steps have to be taken into consideration when you want a precise measurement of the energy involved. So now we're going to come back to the beginning of part 2, comparing oxyacids. And in this case, we want to make the observation that many of our oxyacids can have different numbers of oxygens. And we talked about naming those earlier. It's also on a handout on Canvas. But as you add more oxygens, the acid strength actually increases. And that may seem counterintuitive because you're thinking, well, the more oxygens I have in my anion, the more electronegative it is. And so the more tightly it's going to hold on to the proton. And so the more oxygen should make for a weaker acid, not a stronger acid. So we have to explain why that turns out not to be the case. And the reason that that turns out not to be the case is the fact that the more oxygens your anion has, the more it can distribute the negative charge across all of those oxygens, which actually makes your anion more stable. And if it's more stable, it can more readily lose its proton, and that relatively stable anion then can be in solution. So, for example, if I've got 3 oxygens here, and I want to donate this proton, my negative charge that's going to result can be distributed across the entire anion, whereas in this acid over here, nitrous acid, my negative charge can only be distributed across 2 oxygens, and that's not as stable. The resulting anion is not going to be nearly as stable as the resulting anion over here. And since this is more stable, it's easier to donate the proton. Since this is less stable, it's not going to be as willing to donate it. And again, the more negative your pKa, the stronger the acid happens to be. And this is further summarized again in this chart. And you can see we've got to talk about the energy it takes to break the hydrogen from the hydrogen-oxygen bond, separate the hydrogen from the oxygen. This is the hydrogen that's going to be donated. Remember, we never talk about the hydrogen that's connected to a carbon for reasons that the text explains later. Then the next thing we have to do is transfer the electron in step 2. And when we look at those 2 energy values and add them up, you can see that there's an awful lot more energy involved in ripping the hydrogen away from nitrous acid than there is from nitric acid. And again, you have a more negative pKa, implying a stronger acid. So that's very different from the acids that involve a halogen, or binary acids, because there the primary thing that we worry about is the bond strength. And that anion, which is monatomic, chlorine, bromine, iodine, very easily can be in water. With the polyatomic oxyacids like nitric acid, again, the goal is to distribute the resulting negative charge across as big a anion as you possibly can, which actually makes it more stable. And so that's why they talk about the stabilizing effect of the anion, because you have a big anion with lots of oxygens across which to distribute that negative electron. In fact, it does give you an indication that you should expect resonance here, because the single electron, there's only one electron here that can be working its way around all three of these possible drawings, though it's only one species, not resonating between the three. So in summary, molecules such as the oxyacids can behave as stronger Bronsted acids, that means donating a proton, when the anion created by the loss of your proton is stable. And what makes it stable? It can accommodate that negative charge because it's bigger than whatever it is you're comparing it to. By the way, a little vocabulary word to remember, the formal charge. You take the number of valence electrons minus the number of dots, lone pairs, minus the number of dashes, shared pairs, in order to find the formal charge. And we always want to find the smallest formal charge to find the most stable configuration for or drawing for our polyatomic anion or our molecule. All right, consideration number 3, carboxylic acids. Why are they Bronsted acids? Remember, the carboxylate is when you have a carbon with a double bonded oxygen and a hydroxyl group at the same time. And that makes it a carboxylic acid. Organic acids. So if we look at this picture right here, here we have a methyl group over here, and notice that it's really negative where this oxygen is pictured in red. It's really negative here where the oxygen connected to the hydrogen in the hydroxyl group is. And over here, it's kind of positive. I'll just make a small positive sign. By comparison, these are the hydrogens connected to the carbon, but now it's really positive over here because this particular hydrogen is connected to a very electronegative element, and so that polarity is much greater. And that, therefore, is going to be the proton that is going to get donated. And the reason it can be donated, even though that's a strong attraction, is because the resulting anion that I just circled is large enough to be very stable and hold on to the negative charge across the entire structure. So the hydroxyl group, the OH bond in these compounds is polar, and that's a prerequisite for ionization. You need a very, very polar bond. Now, here's the use of the word delocalizing in a different way than you might remember in terms of metals. When we talked about the delocalized electrons in metals, we talked about the electrons, the sea or ocean or cloud of the electrons that surround the matrix of positive metal nuclei. We said they were delocalized electrons and explained the shininess of the metal, explained the conductivity for both charge and heat of the metal. Well, now we're using the delocalization simply as a word referring to spreading this negative charge across the rest of the particle. Now, in case you were wondering why the acid strength gets greater as the pKa gets smaller, imagine we had a molarity of 10 to the minus fifth, and we made it 10 times more dilute, and we went to 10 to the minus sixth. Well, the negative log of 10 to the minus fifth, which is what the pKa is a 5. And the negative log of 10 to the minus 6 is a 6. And so you can see that when this is getting smaller, by a factor of 10, this is getting bigger. And that's why we say that the bigger the Ka, the stronger the acid, but the bigger the pKa, the weaker the acid. And you're reminded here, again, that the carbons that are connected to the hydrogens don't dissociate very well. They're not very polar. It's like they don't have a strong enough handle to be yanked on. And as a result, the protons, which are these things, are not going to be lost from the carbons. All right, consideration number 4 answers the question, why are hydrated metal cations Bronsted acids? And here we have to remember what a coordinate covalent bond is. And that's when you can share 2 electrons instead of just 1 electron. And that's called a coordinate covalent bond as opposed to just a regular covalent bond, which involves 1 electron. Now we're going to look at these electrons from a different perspective in the next screencast when we talk about Lewis acids and bases. But the point we want to make is that metals, by definition, could use some electrons, could use a pair of electrons, because the metal ions have lost their electrons, and that's how they got to be metal ions in the first place. So if they receive a pair of electrons, that would be a coordinate covalent bond. And when you're receiving a pair of electrons, Lewis would say, well, that's what a Bronsted acid is. I mean, a Lewis acid is. But a Bronsted acid would look at it like one of these protons is going to therefore be given over to here. And, or I should say, what the hydroxide is going to be given over to the positive metal ion. So let me erase that. So let's see what that looks like when we come over to the next page. So here we have the copper 2 ion surrounded by 6 water molecules. And so it would look something like this. Here's my copper 2 plus ion. And it would have a water molecule there, and there, and there, and there, and one on top and one underneath. So it would be kind of octahedral. And when you put it in water, the water molecule, which HOH looks like this, it's got 2 lone pairs. One of those lone pairs will end up being here, and a lone pair there, and a lone pair there, and a lone pair there, lone pair in the front, a lone pair in the back. And now that's what we've got going on here with the 6 water molecules. But then when we put it in water, you can see that what's going to happen is it can donate one of its protons to the water molecule, leaving behind a hydroxide. So now, instead of this being a water molecule on one side, this is still my metal in the middle. Well, that's great. And one in front, one in the back. But now I have a hydroxide over here instead of a water molecule. So we went from 6 down to 5 water molecules, but the 6th spot is picked up with a hydroxide because the proton it used to have is now added to the water molecule to make H3O+. And so the acidity of the hydrated metal ion increases with increasing charge. So if I went from a 2 plus to a 3 plus, it could be even a stronger acid. Incidentally, plus ones are not acidic at all. And that would make sense from one perspective because sodium and potassium ions compounds completely dissociate. So you need a plus 2 or a plus 3 ion for you to attract a hydroxide, like we did here, and donate a proton. And as a result, as the chapter heading was right here was talking about, way down here, was talking about, you're acting like a Bronsted acid because you're donating a proton. Hope that made sense. Last consideration, why are anions Bronsted bases? That means the anion has to, for some reason, gain a proton. And one of the most common studied Bronsted bases is the phosphate. And so if you look at this phosphate right here, here's my PO4 with a -3 charge. There's my phosphate. And if you look at this bond right there, that hydrogen bond, remember hydrogen and oxygen, NOF, there's my hydrogen bond. There's my lone pair of electrons. This hydrogen right here is kind of in a predicament. Which is going to be stronger? This bond to the oxygen, electronegative, or this pair of electrons? Which is going to pull on the hydrogen the most? And it turns out what pulls on it the most is this side and not this side. So the hydrogen in the water, the H plus now, in the water is going to be connected to the phosphate. There it is, part of the phosphate. Now it's the biphosphate ion. And my water molecule, which now doesn't have the hydrogen anymore, is now just a hydroxide. And so we donated a proton. My proton went from here to the water molecule. And so my anion lost a proton, which makes it a Bronsted base. And once again, we're reminded that as your acid gets stronger in this direction, going up, greater pH, your pKa gets bigger as we go down. And that will conclude lesson 6.